Without further ado, I do want to introduce a colleague of mine for many years and a really good friend, Dr. Victor Gensini, who is just, if you knew the severe weather community across the nation, he's a star. I wanted to say you're a rising star, but you're getting too old to be a rising star. So I know, so 40, God, I hate you. He just well known across. They're doing some amazing work at Northern Illinois. We have a number of NIU students here today, so welcome if you're here for the first time. And he's going to be doing, this is going to be a fun day. He says there's a lot of things planned here tonight. It's a fireside chat, so there's no topic. It's just going to be several topics. So, and there's a lot of audience participation and discussion, which we'll get to. But until then, I hope you're cold and from the cold, windy day outside, and we got the fire going and the Christmas ornaments going. So Merry Christmas, first one to tell you. And here's Dr. Gensini.
Thank you, Paul. Yeah, Paul asked me what I want to talk about, and I said, well, I have a lot to talk about, so how about we just have a fireside chat? This is the only online stock photo video that I could pull without breaking copyright fringe, and unfortunately it had ornaments on it, so you'll have to deal with the Christmas tree. I want to say congratulations to the Chicago AMS chapter in general for receiving Chapter of the Year award. That is an absolute phenomenal recognition, and I think that it really, to me, demonstrates the dedication of folks like Paul and Nick and Anna and Patty and those of us who have really tried to bring this chapter back through the years. Right? When I was here at CUD from 2012 to 2017, we really resurrected the chapter. COVID hit, right? Everything went upside down, and now to see it back and now be presenting again is just awesome. So congrats to all of you for that. I'm happy to be here tonight. We're going to have a lot of fun. About half of the presentation is me just telling you what I've been up to at NIU. I'm going to talk a little bit about a field campaign that we did this spring. I'm going to talk a little bit about a new industry center. I'm going to talk a little bit about artificial intelligence and machine learning and how it's absolutely changing the way that we do the forecasting business. And then we're going to have a lot of time for you all to engage. There's going to be a lot of probably laughing and maybe some crying at some point. So let's have some fun. This is going to be sort of a fireside chat, not necessarily a lecture, maybe a lecture for the first half, but that's about it. I had to come up with some alternative titles. So here instead of fireside chat, I was like, I got to do something. So here was my first thought of a talk, Gilbert's hot takes in cold fronts. And I was like, nah, I don't think that's going to work. For students in the room, if you don't know Gilbert Sebensky over here, I first met Gilbert at NIU when he was the staff meteorologist. If it weren't for Gilbert, I would have never learned GEMPAC. And if I would have never learned GEMPAC, the surface maps that you see on the COD weather site right now wouldn't exist. Think about that. How about this one? Smoke, mirrors, and model output. A meteorological confessional. We'd probably need some wine for that. Mostly sunny with a chance of controversy. I think we'll have some controversy tonight with some of the topics that we talk about, especially will AI replace the human forecaster? That is something we're going to talk about tonight. The rules of engagement for tonight, before we get into some of this. This is being recorded. I'll remind you of that. I will also remind you that if you'd like to speak, please get one of the microphones that will be at the side so that we can get your voice recorded for the audio. Be engaged, ask questions, but don't dominate the conversation or I will just cut you off. Gilbert will usher you out if you're not respectful. Okay?
And
Yes, exactly. Thank you, Paul. All right, before we get started, a little bit about me. You probably have seen me around Chicago AMS for many years. I was a former president but way back when, but I was born and raised in north central Illinois, down in the LaSalle, Peru area, if you know where Putnam County is at. Putnam County used to be the largest county in the state, is now the smallest. It does not have a stoplight. The entire county is very rural. I went to a very small high school, did not have football, about 300 students total. I think there were 63 students in my graduating class, so incredibly small. A tornado hit my high school, and that's when I changed my career path from engineering to atmospheric science. I went to community college down in IVCC, Illinois Valley Community College. I really solidified my love for atmospheric science there. Transferred to NIU. I met the faculty there, fell in love with NIU, and really the rest is history. I did my PhD, I came back to COD, and I was always sort of had a Midwest lean to me. And like many of you in the crowd, I am an extreme weather geek. This is my perennial Halloween costume. I'm sorry for all of you folks in Synoptic. You're going to see me probably wear this again. I am always a frontal system for Halloween. It is typically the time of the year when we start getting some of these stronger extratropical cyclones around here. I wear a lot of hats professionally. Since this is an AMS meeting, I want to just let you know some of the things I do within AMS. I'm an editor for one of the journals, the Journal of Applied Meteorology and Climatology. There's also another journal called Weather and Forecasting. I serve as an associate editor for that. AMS has what are called STACs, Scientific and Technological Advancement Committees. I've chaired the SLS stack for quite a while, and I'm also on the Weather and Forecasting stack. The upcoming conference in August, the Severe Local Storms Conference, number 32, will be in Madison. I'm helping co-chair that. It's going to be a lot of fun. Students highly encourage you to attend these types of professional development meetings. It's a great way to build your professional network and hear from leading minds in the field in terms of the cutting edge science of what's going on. I just got back from a week-long trip in Boulder. I'm on the NCAR, the National Center for Atmospheric Research, their mesoscale and microscale meteorology division advisory panel. I'm on the AGU Experts Guide, and I'm also a non-resident scholar at something called the Insurance Information Institute. That's a lot of hats. I don't get a lot of sleep. But as you'll see, it's a really good thing, and that III thing at the bottom is going to come in really, really important when I talk about some of the work that we're doing on later. Okay, this is the agenda for tonight. I'm going to try to go in order. I'm going to try to get through everything. The first thing is going to be a lot of fun. It's just going to be me telling you a little bit about what we did this spring at NIU and across about 13 other universities. The second part, I'll probably lull you to sleep a little bit, but it is a very important and interesting initiative that we have going on between NIU and the University of Wisconsin. And then we're going to get into the saucy stuff. We're going to talk a little bit about AI and ML and weather forecasting, what we need to do better to train the next generation of meteorologists, including many of you in this room. If we have any Weather Service colleagues in the room, I think we'll talk about this anyway, the future of the National Weather Service, which could get turned upside down in the next couple of years, and also when good forecasts fail, which is something that we saw earlier this year in July in Texas. And so hopefully we can cover as many of these as possible. Let's jump right in with ice chip. How many of you have seen hail larger than 2 inches in diameter? So like larger than a golf ball. Okay? How many of you have seen larger than a baseball? Larger than a softball? Okay. That's because you were on ice chip. There is, by the way, if you're not familiar with hail and hail damage itself, there's a lot of damage done every year by what we call severe weather, right? Severe convective storms. About $60 billion actually in losses every year. And a majority of that is due to hail. And we don't know a lot about hail. We don't know how, some cases, how hail forms. A lot of people like this idea of the hailstone going up and down in the updraft, and that's how you get all these layers. That is not true. It is not how hail forms. It is not how it gets those beautiful layers that we see sometimes. We have all of these really cool scientific questions when it comes to hail specifically. And so that is not necessarily a problem. It's an opportunity for science. And science is, of course, driven by the scientific method. And what's the very first thing in the scientific method? Get observations. So the goal of any atmospheric science field campaign is to go get observations. Well, where is our laboratory? Our laboratory is where? Outside. So we have to go to the thunderstorms, in this case, to the hail, to gather these observations of things like density, compressive strength. How much kinetic energy is there when a hailstone hits that's the size of a baseball? These are all questions that we don't really know the answer to, and ice chip was born. This was an 8-year, this basically felt like raising a child for 8 years. Combination of government, academia, and private sector partners that are shown at the bottom left there, the really tiny logos. The coolest logo of all is the ice chip logo, and we have Diana to think of that. She's in the room tonight, former COD student and amazing graphic designer who helped design the ice chip logo. What you see here in the picture from the drone are all of the students and principal investigators, so the faculty that took part in IceChip. This was a picture in Boulder before we left. The National Science Foundation was the primary funder of this campaign, and we were out for 42 days in the field. Now, those of you who have storm chased before, right? How many of you have storm chased with CAD? How long are your trips? 10 days. Are those pretty grueling by the time you get back?
Yes.
Okay. All right. How about 42?
No thanks.
All right. I did laundry 5 times on the road. All of those little tracks that you see across the Great Plains, each of those is a different day. Overall, our vehicle, the vehicle that I was in, did about 16,000 miles across the Great Plains. We spent a lot of time in Texas. That is usually where the large hail is at early in the season. But at one point, we were about 100 kilometers from the Mexico border and 100 kilometers from the Canada border. So we made a lot of distance covered over the course of 42 days. This is basically from about mid to late May through the end of June. And you can see 74 students got the opportunity to participate in this field campaign. So this is collecting data observations, running radars, launching weather balloons, measuring hail. Our largest hail was 149 millimeters. For those of you who are not metric to inches, that's about 5.9 inches, so just shy of 6 inches in diameter. And I think, what was the weight? 1 pound? 1 point something? Was it 1 pound? I think it was, the mass of that hailstone was just under or just over 1 pound in terms of its weight. So you don't want to get hit by that.
What's the terminal velocity?
The terminal velocity of that hailstone, I mean, you have to measure, try to calculate it, but usually those hailstones can fall between 40 and 50 meters per second. So you get hit by one of those, yeah, watch out. All to say, this is all in the name of science, and everyone you get back to DeKalb or you get back to Chicago, and everyone's like, well, what did you find? I'm like, no, that's step one, right? Step one is gather all the observations. Now the hard part begins in analyzing all of this data. I'm going to quickly just tell you some of the measurements that we took, and then I'm not going to get into the science hypotheses tonight or any of those questions. I just want to basically show you some pictures from the campaign and what we tried to capture. One of the most important thing on any field campaigns is to capture the atmospheric base state. We need the base variables: pressure, temperature, right? Mixing ratio, U and V wind, altitude, those sort of things are really what drive our weather models. And so we have to be able to take these measurements near the hailstorms to better understand the environments that these storms that are producing hail form in. So we do that with weather balloons. We had full tropospheric launches. We also had something called wind sondes, which they basically measure the lowest 1.5 kilometers. These little mesonettes are these, well, Kelvin, you tell me what you guys call these what? Pods? Mesonet pods? So you drop these, they log temperature, pressure, humidity, wind speed, and wind direction at a fixed location. We also had driving versions of these. So there's these mobile mesonet trucks that we drive around. They take measurements as you move, so you can kind of be more of a Lagrangian tracer rather than a Eulerian sort of perspective when you're near these storms. These particular instruments were supplied by the University of Alabama in Huntsville, their farm fleet. If you are not a meteorologist in the room and just here by chance, the reason that we take these weather balloon measurements at all, and they're happening in general twice a day from all over the globe, they drive our weather forecast. So at 9 o'clock news, if you watch Demetrius Ivory on WGN, right, that forecast is coming from a global model, which is initialized with weather balloon data. And that's why not many months ago, when we're still losing, it seems like every day, more and more upper air observations, there were many of us that were getting very frustrated and very vocal about the need and importance for upper air weather balloon launches because they do drive our weather forecast. Without weather balloon data, we would not be able to make a skillful or accurate prediction in terms of weather forecasting. So these types of weather balloons are really our only vertical profile that we typically get other than aircraft. But aircraft observations are very slanted in terms of the amount of horizontal distance they cover versus the vertical. We also had quite a few radars, 4 to be exact. One of them is the one in the video shown here. This is called the mobile cow radar. It's a mobile C-band, so it doesn't attenuate as bad as X-band does. Typically, the mobile Doppler radars are X-band radars. This radar, though, has a giant crane on it. because you actually have to set the dish up. You can't drive with it because you'd hit the overpasses, right? So let me spin this around again. It takes about an hour and a half to set this thing up, assuming ideal conditions. If it's windy, it's much harder. But when you do get it set up, if the storm passes within your domain of your radar, you get some really high resolution C-band data, which is really important for understanding things like hail reflectivity, scattering, properties of hail in the vertical column. So we can do all kinds of different scanning strategies with these radars to better see inside. When we're not close to an 88D, right, we need good radar data. So we had 2 mobile C-bands. We called them COW and the mini COW, and then DOW A and B, which were both X-band radars. And if you use these and position these strategically, you can actually scan the storm at the same exact time if you sync their beams, and you can recreate the 3-dimensional wind field if you do that. And one of the things that is so important about recreating the 3-dimensional wind field is understanding the updraft, the vertical component of these storms. So, right, if you're only scanning one radar, we've all looked at Doppler velocity before. It's pretty, but you just have this 2-dimensional view. If you do dual Doppler analyses, you can synthesize this. It's almost like stereoscopic view. For those of you who ever remember GIS, right, you're looking down under a stereoscopic lens. You can do that with a radar and get that 3rd dimension. These are really cool. These were developed by the Bureau of Meteorology in Australia. These are called hailsons. These are essentially twister. This is the idea of let's get those little tiny balls, let's get them into the tornado. Let's get them into the storm. In this case, they go up on a weather balloon, and then once they get into the updraft and you start seeing the vertical velocity increase, you immediately cut the balloon. And you allow this styrofoam little object that becomes basically just this Lagrangian particle, this drifter. It gets caught in the updraft, and it has an accelerometer in it. It has GPS in it. We can measure its speed, its velocity, its positioning, and it tells us essentially this is the track that a hailstone would take within a storm. And if you can go recover them, which I think our teams did recover quite a few of these during the campaign, they can tell you a lot about hailstone trajectory. And I will say that on many days I was kind of what we call the field coordinator that was sort of leading, like, here, you need to go here, you need to go here. It was more like I was more like air traffic control during the campaign. We had one day a hailson measured an updraft of 78 meters per second. Okay, now if you go back to the old Morrison and Weissman and Klent papers of supercells of years past, like, we were thinking maybe 30 meters per second would be a general thunderstorm updraft, right? And then there was some research by George Bryan and others, and hey, maybe it's more like 60, 78. Okay, maybe the updraft is a lot more powerful than we think it is. Okay, so I'd love to see more and more of these hailsons released in storms. I think they can tell us a lot about the vertical structure and updraft speed. So that's something to think about. Yeah. Right here. Okay. Yeah.
It's on, hopefully. Oh, thank you. Question, 78 meters per second, was that in a severe thunderstorm updraft or just what we call a general thunderstorm updraft?
That would have been in a supercell. Yeah. And we think those types of velocities are probably reserved for supercells which have mesos and vertical pressure gradients. Yeah. Other things that we were doing, obviously we cared about hail at the ground. We had impact astrometers. These are basically, they look like tripods with instruments on them, and as the hail impacts them, we record the impact. And we can back out the hail size from its kinetic energy and its impact, and we just laced the road with these, right? Wherever we thought the hail swath was going to cross the road, we'd put all of these instruments down. We had Parseval distrometers, those are shown in the middle. Those do not use impact, those use lasers and optics to understand hail size distribution. And then of course, we did a lot of measuring. Where's Katie? Katie was in my vehicle, and we just, literally our job was to drive around and measure hailstones. It was a lot of fun. We measured a lot of hailstones on the campaign. And we really wanted to document the swath characteristics for the first time. Really, really exciting. Here's what those impact astrometers look like on the left. So you can only imagine storm chasers driving by those, and they were probably like, what in the world is that? And yeah, that's what they look like. We laced the road up and down, every 100 meters or so in some cases. And then on the right, we actually used some old technology, hail pads. Right? These are basically styrofoam pads that we put down every so often. We mark their GPS position when we drop them, and then as the hailstorm passes over, it impacts that styrofoam, and we can see exactly the size. Because sometimes you don't get there, sometimes you'll get there and there's no hail left, right? It's all melted. So that can be a challenge when you're trying to recover hail in these things. One of my favorite instruments on the campaign was the UA, the Boulder, CU Boulder has the Raven team. This is basically a drone that had several cameras on it. One of them was pointing downward, and we could measure hail size distributions from the drone. So we get this really quick fly, right, across the swath and back across the swath, and we can see exactly where the aircraft was on its plotting radar there, and then that gives us an idea of, okay, this is what we were seeing at the ground, but here's the actual spatial dimensions from start to finish of that swath. Is really cool. Another really neat thing, and this is something that still baffles me today, all of these hailstones on top were from the same exact storm picked up at the same exact location. And look at the variability. The variability is incredible. We have, for those of you not familiar too much with hail, so hail in general is always at the middle. You'll find something that kind of looks like Dippin' Dots. It's called graupel. Graupel is basically the nucleus for hail. And then if you have a white ring, that's what we call dry growth. So that's just forming at a very specific temperature where the water freezes to ice, and it happens so quickly that a lot of air bubbles get trapped. And so it looks like it's opaque. And then you get this much smoother, kind of more clear appearance. That's called wet growth regimes. These are just happening at different temperatures and at different accretion and freezing rates in some cases. And so look at this. This is all from one storm in one spot. And what that tells me is there are so many different pathways and trajectories that hailstones are taking, and they're landing at the same spot, which is amazing. So you got to almost think about the backwards trajectory of how did the hailstone get to that location. And so we have many of these, thousands of these hailstones saved. They're at NCAR's cold lab, and we'll be cross-sectioning these things with a bandsaw and then measuring their water vapor isotopes. So we'll be able to see exactly where that storm was. Okay, maybe this ring right here formed at -12 Celsius. We'll know exactly the temperature that ring formed at, and then we'll have the weather balloon data to pair back and say, oh, that hailstone was at -12 C and it was exactly 14,000 feet. It's going to be amazing when we're able to pair some of that stuff together. You guys want to see something cool? You guys want to see something cool? It wasn't cool already, she says. This picture that I'm about to show you, there's probably only 250 people in the world that have seen it. Now, how many people? There's 8 billion people on the planet, right? You're one of 250 people that have seen this. Okay, look at that. That is cool. That is heart eye emoji cool. Okay. That's a thin section of a hailstone. It almost looks like a tree. Tree ring, doesn't it? A geode. Yeah. Funny how nature repeats itself in many different ways. Beautiful, right? Oh, hell yeah. All right, that is a high resolution. Basically, we supply light from underneath the thin section, and you get to see the detail of all of those wet growth and dry growth regimes that all look like different rings on a tree. It's amazing. And so you can imagine the detail, the level of detail that's going to be required to go grab water isotopes, from each of these rings to figure out exactly all those layers. So a lot of folks in the cold room will have their work cut out for them, but that's the type of stuff that we were able to collect on this field campaign. Absolutely remarkable. In terms of density, this is just a sample day. You can kind of get an idea of how often we were stopping and looking for hail. I don't have a scale marker on here, but the general road network, these are about half-mile grids, so some of the roads that you see here. So we were stopping pretty often, and we created this little app on our phone where we could stop and save our GPS location and take pictures, and then you see the hail size over here on the left. So we were getting pretty high density measurements, and we want that because we have higher resolution radar data, we have this disdrometer data, we want to be able to see what is the variability in distribution and size as we go along these hail swaths. Here's one other example from June 6th. This was one of our more successful IOPs. This was the day after the Morton, Texas tornado. You can see hail size from kinetic energy on the left, and then we overlay the radar reflectivity on top of it. So this is, at the end of the day, hopefully going to improve things like mesh. How many people are familiar with mesh? Maximum estimated size of hail. Right? That algorithm is not very good. And one of the things that we want to do is improve mesh by taking some of these radar attributes, ground verifying them at a very high spatial and temporal resolution, and then being able to say, no, this was the radar reflectivity, or this was the actual area of the storm that was producing the largest hail. And I will say there were definitely cases where I was watching level 2 radar, or I was even watching some of the Dow radar, and the hail that we were finding at the ground, you would never have put it there. You would never have said that's the largest area of the storm. You always gravitate towards the higher reflectivity, right? But in reality, some of the largest hailstones that we found, especially with supercells, were in the rear flank downdraft or right along the gradient of the forward flank. And it was actually remarkable. This case is a little bit different in some ways, but I can't. I was like, there's no way you're finding 4-inch hail there. Yep, I pulled up, I verified. There was definitely 4-inch hail there. So we've got a lot to learn in terms of what the radar is seeing and telling us versus what we're actually finding at the ground. Here's some more pictures. On the left, that was a typical day. You know, pretty remarkable. There's our largest hailstone of the campaign in the middle. That was the one that was about 5.9 inches in diameter. Yeah, and then again, golf balls, just kind of run-of-the-mill stuff. So, okay. On to number 2, then we're going to get into the saucy stuff. This is something relatively new that we're standing up at NIU. You can see the logo there. Again, thank you, Diana, for another beautiful logo. She does a great job. Isn't that cool? It's like a tornado in the middle of the cloud. I love it. CIRCS. CIRCS stands for the Center for Interdisciplinary Research on Convective Storms. How did this start? In May of 2023, when we still had a functioning government, NSF and NOAA partnered up together to basically say we have some very challenging problems that are crippling insurance and reinsurance. If you own a home in Florida right now, you're probably paying more for your insurance premium than you are for your mortgage. If you're in California, you probably can't even get wildfire insurance. And if you're in the Midwest, and if you have a state farm policy, you're probably now paying twice as much as you are for your premium than you were last year. Why? Why is this happening? It's a multifaceted problem that involves politics, it involves exposure, vulnerability, changes in our climate, changes in our weather, and it's not going to be solved overnight. NSF and NOAA realized this, and they basically said we need to do something about it. And part of this actually was stemmed out of the insurance industry. It had nothing to do with NOAA, it had nothing to do with NSF. Industry was coming to NOAA and NSF saying we have a problem. Okay? NSF created this call. It says, come up with your IUCRC. IUCRC, for a lack of a better term, is an opportunity for industry to work with academia and government together. So it's like a consortium, okay? Where industry pays membership fees to be a part of the center. Those membership fees fund students to do projects and work with the goal of creating data sets, knowledge, and products for industry. So it's a kind of a cool thing. There's only one other center that exists right now that is kind of in the geoscience space, and that's out at San Jose State. It's called the Wildfire Interdisciplinary Research Center, or WIRC. So we saw that come out in 2023, and I immediately said, convective storms, hello, 60 billion every year in loss, big time losses from hail. Here's the growth pattern for severe convective storms over the last couple of decades. Notice the step function in about 2008. Now every single year in the US, we have at least 10 of these billion-dollar disasters, and you can see they're growing in terms of not only their frequency, but their overall impact. Last year, through Q3 in 25, we had 60 billion in severe convective storm loss. So there obviously is a trend, and we thought it was a very, very ripe time to pitch one of these IUCRC centers. We know that they impact our community. Here's Joplin High School before, and Joplin High School after, right? We all understand the damage that tornadoes can do, that hail can do. Hail is actually way more costly than tornadoes because it's way more frequent. Derechos, believe it or not, have become incredibly expensive. The costliest thunderstorm in United States history is what? Anybody know? The Iowa derecho, the Iowa 2020 derecho is the costliest thunderstorm in United States history now. That's a derecho. Right? Total for that particular event was, don't quote me, but it was 12 billion alone. Okay? So, and that's not, I don't think that counts agriculture. That's not counting agriculture. Okay? So these can be incredibly expensive events, and so we pitched this center called CIRCS. Okay? CIRCS is a partnership. It's a partnership between universities, in this case NIU and University of Wisconsin. Industry, you can imagine what industry cares about this. It's insurance and reinsurance. And the government. NSF and NOAA provide some funds to help facilitate the center. The whole goal of IUCRCs is to basically take startup level fundamental research that could be transformative and trying to get it to a point where it can be integrated into commercial deployment. So we're kind of focused on this ground level, startup level methods and data sets that can be eventually integrated into industry workflows to help them address the pressing needs of convective storms. We had to go through this entire process. I had to go through a boot camp. It was cool. But I went through a boot camp training on how to run these centers. We pitched our proposal, and I'm very happy to say that as of last August, we were funded. And our very first, thank you. Our first meeting is coming up in November. Here were some of the companies that participated in our planning meeting. You can see, you probably recognize some of them. Many of the larger mutual companies, but also some very large reinsurance companies, catastrophe model vendors, data, insurtech startups, all very, very interested, some even nonprofits, interested in what this center potentially had to offer and to bring. And so again, these companies will be paying a membership fee to join the center, and those membership fees will all go into a big bucket. And then all of the different faculty members and students can pitch projects. It's very much like a Shark Tank style format. So you get to pitch a project and the companies get to vote on it. And that's what will be funded for the year. We did our nails. We painted the logo, Diana's beautiful logo on the wall. And so here's, if you want to check out our new website, it's at circs.niu.edu. You can go take a look at the website and read a little bit about what we're doing and the companies that will be joining. And our first meeting is coming up here in November, so I'll be able to report out on that to some of you at next meeting. The most exciting thing to me is that this is not a one-off project. This is something that I now have a budget and I can plan. And when I can plan, I can think about horizons and student needs and who I might bring on to do these types of projects. And so for the next 5 years, we're not only going to design research projects, but we're going to support students at both the graduate and undergraduate level. We have a lot of students that are already on the table to be funded by these types of things. A big component of these centers is workforce development, training the next generation of students to be able to work on problems in applied meteorology and climatology. And that has always been our staple at NIU, and this just, I think, reaffirms some of the important work that we're going to be doing. And then finally, hopefully, with some of the projects, we can push forward the needle on the understanding of what are some of the major drivers and factors behind the trends that we're seeing and help people be a little bit more resilient when it comes to their book of business, their policies, and also the potential for the future on the change of those portfolios. All right, we're through the fun part. You guys ready for this? This is going to be so much fun. Okay. AI, so that's artificial intelligence. ML, machine learning, they are not the same thing. You might be asking how they're different. We can talk about that later. But how these two things, which are certainly buzzwords right now across all different areas of weather and climate and really all fields in general, and weather forecasting. So what I need you to do for this is to take your phone out and scan this QR code. If you don't want to participate, that's fine, but it'll be a lot more fun if you're engaged and you answer some of the questions that will be coming up here. You can, if you can't scan the QR code, you can just go to polev.com/VictorG400. That's going to get you to this page. So let me go over to my internet browser. And you should be seeing something on your phone that looks like this. It might say, in one word, what comes to mind when you hear AI and weather forecasting? So start answering those. and we'll see what we get. Hopefully this is going to be a word cloud, but I'll give you all a little bit of time to respond, and then we'll take a look at some of the responses. And this might also be a good time to make sure that we have our microphones ready to go, because I'm going to ask some people for particular thoughts as we see some of these come in. Unemployment? Yes. Uncertain. I agree. There's a lot of uncertainty right now. A lot of potential. Okay, I was hopeful that this would come up as a word cloud. It doesn't look like it's doing a word cloud. It's just giving us all. I'm interested in the individual that put in dangerous. Anybody care to elaborate on the danger aspect? Microphone? Who wants to be the runner on this side? We need a dedicated runner. Okay, Gilbert, go ahead.
Yep, I'm the one.
And let's try to keep our responses from like 30 to 60 seconds, because we have a few of these activities for the others too. I don't want to run out of time tonight, so yeah.
It can be dangerous because in a number of cases I'm seeing outside of the meteorological realm, AI replacing thinking, and that's why I think in that aspect it's dangerous.
I think that's a fair point. Yeah, go ahead. Are you running for us? Okay. All right. I thought you had some. Okay. Incorrect errors. Wow. Okay. All right. I want to see if I can synthesize. Let me see.
I think one thing that could be dangerous about AI as well is the fact that it hallucinates data. Like it kind of comes up with something that doesn't exist, which could be really bad for weather forecasting. It could be for false alarms and then hallucinate something that, like, hallucinates that nothing is there when there is something that's there.
I love that response. You're going to see that a lot of AI and weather forecasting relies on training data, training models. And there's something called the black box that we're going to talk about as well, too. Go ahead.
So, kind of just going off of that, the whole thing about hallucinating data, something I remember, it was Kevin Doom and Kevin D'Onofrio came by NIU a few months ago, and this is something I talked about with them. The thing I think I'm a little bit more, like the most apprehensive about with AI forecasting, specifically in NWP, is that the importance of being able to understand what's going on under the hood of that model is critical to being able to make an accurate forecast, and that's just something that we simply can't do with AI numerical weather prediction because nobody really knows how it thinks.
What if I told you that AI has been around in weather forecasting for decades? Would you believe me? Yeah. Anybody know how? In what way? MOS. Model output statistics is machine learning, right? That is a form of machine learning. Lots of these different types, if we're getting away from deep learning and we're talking about simple statistical methods, that's really all machine learning is. It's neural networks, it's things that have been around for a long, long time that are now just getting to the point where they're fast enough, they're cheap enough to use, and they're being leveraged on these very, very large data sets. So there have been some aspects of machine learning that have been around for a long, long time. And I can tell you, when you hear danger, well, you'll see. How many of you think you could beat AI on a day 4 forecast? How many of you think you could beat AI on a day 1 forecast, so tomorrow's high and low temperature? Okay. Every year, there's about 1,500 students that participate in something called the Weather Challenge. It's basically a competition to try to see who can make the best forecast. Out of those 1,500 students, only about 100 every year actually beat what's called the USL model, which is basically just a MOS, machine learning type of model, right? What does that tell you, right? You can still win, you can still be better than, but for a majority, the answer is actually you're probably not better than some of these tools, okay? All right, let's move on to the next one, and then we're gonna do a lot of this kind of stuff. Here's some forward thinking. Back to your phone, you should see this now. By 2035, I don't even know if I can think that far ahead right now, which group will produce the most accurate weather forecast? If your answer is not up here, I just threw a couple in. I'd love for you to take the mic and tell me what you think or what group would be the most accurate at producing weather forecasts. So I have human forecasters using NWP. That's essentially what we're doing now. Artificial intelligence machine learning trained on reanalysis, traditional numerical models themselves, or human hybrid AI systems. There might be, is there E? Oh yeah, sorry, I don't see, I'm not scrolling down all the way there. So private sector AI, so these would be the forecast nets, the deep minds, the models that are essentially coming, seems like a new one is coming online every day. I agree with you, it's D. It's going to be human hybrid AI. How many of you would get in a plane right now, 737, and take off without a pilot? Probably not many of you. But did you know that plane could take off and land by itself if it wanted to? Okay.
Victor,
So you
how
get the analogy here, right?
How
Go ahead.
concerned would you be the longevity of that? I mean, I think maybe we all, clearly we all agree.
Yeah.
But the longevity of it, I mean, because you're talking about pattern recognition, right?
You're
When
talking
we
about
teach pattern recognition. At some point, if we're relying on these systems, we stop like recognizing pattern recognition. We get worse at it. If we're
absolutely.
relying on them.
This is a conundrum that we have with training students as meteorologists. It's something that we're all going to have to deal with. And instead of being maybe forecast interpreters of reading the tea leaves of the models, and so we're now trying to figure out how can we program these things, right? And how can we leverage them in situations where we know they might be able to fail. And so we have to recognize their weaknesses, just like NWP has its weaknesses. These human hybrid AI systems are still going to have weaknesses. And guess what? You can't have the AI system without the traditional numerical model because you still need data assimilation. You still have to create t minus 0 or t equals 0 before you can step out into time. Yeah, you don't have to solve the base state equations. You don't have to do the differential equations anymore with the AI systems, and they're a lot faster, as we're going to talk about later. But the human hybrid AI systems will absolutely be, and they're already in the private sector, will be the wave, I think. Those groups will not only have the most accurate forecast, they'll be the fastest forecast to generate, and they'll actually be the cheapest, you'll see here, in terms of computational need. And a lot of the other stuff, like traditional numerical models, we might not be talking about things like that in even 5 years. That's how fast this stuff is evolving. I know we're always talking about what's the new version of the HER, what's the new version of the European. That might be done with in a couple years. We might not be talking about physics-based models anymore because I have some stats to share with you about how scary good these models are. Okay. All right. How about this question? It doesn't matter if a forecast is a black box. In other words, you don't know why the model is saying what it's saying as long as it's accurate. In other words, who cares how you got to the answer as long as the answer is right? Do you agree with that statement? Strongly agree, neutral, disagree, or strongly disagree? There are vastly different camps of thought on this. Right? Most of you are in the disagree to strongly disagree camp. Who wants to elaborate on that answer? Paul?
As a teacher, my God,
Yes.
it better be disagree, right?
Yes.
Again, it's the human mind, especially if what you said in the previous question, that it's a hybrid. And the only way a hybrid will work is if the human mind stays with it and learns from the machine learning and learns from AI and advances. And I do fear what Evan said. People become lazy and they stop thinking about what's actually happening and have no idea. I do want to bring up one thing from Chuck Doswell, what he said many, many years ago. It's about value added.
Yeah.
You don't have to beat AI on high pressure systems, but once in a while you need to beat it when their value that you add is significant. And I'm hoping we still can do that, but not unless you keep up with what's going on.
That is a key point we're going to come back to later. There are still times when you can beat AI, and you can beat AI big time. And it usually involves the day one convective forecast. Yes.
I want to point out that this situation has already come up many, 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 many times. And where it's come up a lot is in transportation modeling. Now, in transportation modeling, they have to what everybody else thinks as a black box, but it's gotten so slick, so automatic, so whatever, that even the engineers don't understand what the heck they're doing. They're just punching in numbers. Sometimes it takes somebody like me, an old-fashioned, can't stand computer programming person, that actually understands what the model is doing to catch them at their trouble, especially if they're trying to tweak the model to get the output that they're expecting. That's a dangerous one.
Said. Very well said. I am in the strongly disagree camp. I think we absolutely need to understand why the model says what it's doing. Otherwise, how do you know when it possibly is going to give you some bad advice? There's no guarantee that that forecast is always going to be accurate. When it's accurate, yeah, it's great, and you're going to come back to it because it's reliable. But if you have no idea why the model is telling you why, the beautiful part about machine learning and AI right now is you can also integrate in what's called explainable AI, and you can ask the model why it's predicting what it's predicting. And it's something actually that goes back to game theory. Game theory is basically the idea of if we have all of these individuals in the room that are all contributing to a forecast, so all of you are little different predictors, and all of you are going to contribute in some way to understanding what the forecast might be tomorrow, over lots and lots and lots and lots of repetitions, I could see which of you were the most important to getting the answer right? And then we could value your contributions to the forecast. And then I could basically say, oh, tomorrow the forecast is going to be 92 because Paul Servakis said it was going to be 92, and he's been right the last 35 times. Right? We can actually use game theory, the contribution to the forecast, to see, oh, it's CAPE that's driving this, or it's precipitable water that's driving the amount of precipitation tomorrow. You can actually use tools like explainable AI to do this. It's just not everybody is doing it, and it makes describing these models much more challenging. Maybe one more comment before we move on to the next. Gilbert.
Real quick, if you get a forecast out of AI that is absolutely correct, it could still come up with the answer and be absolutely wrong with how it got there.
Sure, absolutely. You can get the right answer for the wrong reason. There's no question about that. Okay, next question. Oh, this is fun. Okay, I almost put an abacus on the very end over here, but if you don't know what that is, that's good. That's a slide rule. Click on the image about approximately, imagine this is a timeline from the start of meteorology and slide rules to all the way today, which is GPUs and AI weather forecasts, and then go backwards from the 90s, WXP in the 80s and 90s, and the advent of the web, and then DieFax and punch cards and ENIAC. We don't have anybody here from the slide rules?
Hey, Paul hasn't heard yet.
You did slide rules? Yes! Wonderful. Okay. Obviously, those first three are not like in perfect order, but it was kind of funny, and I didn't want to put an abacus up there because I thought that would be like dinosaur esque.
Now you're talking.
Okay. Awesome. We've got some eclectic. I'd like to hear some people and their perspective of AI and the changes in revolutionizing enforcement. Again, 30 to 60 seconds from the DieFax era. I entered about right here. I'm on the border of maybe the first COD web pages showing up in the mid-90s, and then obviously have seen my career over this span. But WXP was the major graphics package then. I've seen a lot of change since then, and I know you've seen it too. So I'd like to hear some people. We're going to talk a little bit now. We're transitioning into that third topic, which is going to be workforce development. And so I'd like to hear a little bit about a story or something funny from when you entered meteorology.
Well, I don't like showing off my age, but I started out with Roman numerals.
You know, Victor.
Well, I mean, yeah, that's.
It's kind of interesting on because I put on the DieFax, even though we actually had punch cards once.
Okay.
At the very end, but every time we did something like a DieFax map and saw an improvement, at least early on, I was always like, "Ooh, I want that." And that's what kind of motivated us. We knew the shortcomings of where we were and wanted the next step. And so I think it would be foolish if we didn't say, AI is the next step, and machine learning. We need to go there because it is going to make us better. But I want to make sure that the people they want to go forward because it is going forward.
It's going forward and it's already here. And I'll demonstrate tonight that it's already here. In fact, I want to share something with you before we go on to the very next topic, because I want to underscore where we've gotten in just the last year with this stuff, okay? This is how fast this stuff is happening. This is truth. Right now, an AI model running on trained and running on a GPU can make a global forecast for 15 days by the time you can walk from this room to your car out in the parking lot, okay? That's a 15-day forecast in about 15 seconds. So now imagine I tweak the initial conditions. How fast can I get a 50-member ensemble? Pretty quickly, okay? In addition to being fast and actually computationally cheaper, because it's a GPU, I am now beating you in almost every single flagship model verification category. 500 millibar height, precipitation, temperature at the surface, all of these verified things that we use to benchmark our models. I'm faster than you by orders, and really an order of magnitude, and I'm more skillful than you, or at least as skillful as you, okay? That's truth. That's happening today already. It's not true for every single spatial scale, okay? So as you get smaller and smaller scale, convection allowing, getting down to tornadoes and stuff like that, it's not as skillful as, say, some things now. But for most forecasting applications, AI has already shown it can beat traditional numerical weather prediction models. That is a truth. Here is another truth. Look at this. Look at this. The GraphCast, Pangu, and European APHIS right now are outperforming the European deterministic model, again for some of those, in nearly every single large skill category of metric. At ECMWF, their operational AI model has matured into their operational stream. You're now seeing these products online. People are producing them, right? If you go to weather forecasting sites, you can see all of these models available and presented, and they look just as good as the operational typical NWEP output does. Google's DeepMind's GenCast right now, they're actually outputting some data up to the minute scale, right? Because it's so cheap to produce these forecasts over a 15-day period. And even in some cases, the models that are looking at very high resolution, like comparable to the high resolution rapid refresh, the HER, are actually showing skill forecasts over the HER. The biggest challenge right now for convection scale, so thunderstorm forecasting, is that we don't have a good reanalysis data set. For synoptic applications, we have ERA5. So all of these other models are being trained on ERA5. And again, I get the reanalysis data, I say go. I have a 15-day forecast in 15 seconds on a GPU. Okay? And it's just as good, if not better, than the operational ECMWF model. That is fact. How much faster? Look at this. On an NVIDIA A100 card, ForecastNet produces a 24-hour forecast in a quarter of a second. Okay? Quarter of a second. Operational AI, 1,000 times less energy and 10 times faster than their physics ensembles at ECMWF. Less compute, less energy used. Super resolution downscaling, this is not verifiable, it's not in the literature right now, but NVIDIA is claiming that they can save up to 10,000 times energy taking away things like the HER for kilometer scale prediction by using these high resolution models. And I believe it. I think we're there. I think as soon as we get a high resolution reanalysis, it's over with. You're going to see a lot of these models starting to be retired. And you're going to start getting super ensembles, right? The trade-off's going to be you're going to have a 100-member ensemble that runs in the matter of 10 minutes. Right now, if you go to the COD webpage and you wait for the GFS to come in, if you look at the timestamps on these images, 3:34 to 5:16, you're waiting about an hour and 45 minutes for the entirety of the GFS to come in. I can generate it for you right now in 15 seconds. Same forecast, just as skillful, right? Over every single metric, right? That is an absolute game changer. Okay. Anybody want to make a comment on?
So,
yeah.
Victor,
And then we're moving into workforce. Sorry. We're already, God, I knew this was going to go
Just
over.
before we get too far ahead, something I wanted to ask is, if you go back to you're saying the AI models are just as, if not more, skillful than current physics-based numerical weather prediction. Something I'm curious about is, how does AI handle extremes?
Very good.
It's good.
Very good. Yeah, you would think if you have a training data set, you're not going to be able to get anything outside of them, but we have now what are called physics-informed AI models, so they actually do still understand the physics after you produce that field, and they're hitting the extremes just as often as they should be. There's no like missing large white, black swan, long tail events. They've been trained and calibrated to be able to produce those types of forecasts. We're there. We're way past that, in fact, in some cases. All right, let's hop back over to, and let's see, we went through that, 2035. We did our little thingy. Let's move on to, this is more workforce development. So this is relevant for you. Are you guys still seeing this okay on your phone? Yeah. Okay, good. I try to hammer this home with every student that I get in touch with, and Paul and I have had so many conversations over the years as to what it means to be a meteorologist in 2020 and beyond. And it's not what we're training students to be. We're still training students at university how to be a meteorologist in the National Weather Service. The modernization of the Weather Service, right? I mean, that was what we did. We were producing forecasters in the National Weather Service. Most of my students now are not going into the National Weather Service. They're going into catastrophe modeling. They're going into insurance, reinsurance, weather and climate analytics, supply chain logistics, consulting. That is not what we're training you to be, right? We're training you synoptic meteorology and mesoscale, right? So what do you think the most important skills are going to be to stay relevant? It's not that difficult, right? It's going to be coding and data science. In fact, if you have not learned a computer programming language, at least one, by the time you are like halfway through your undergrad degree, you're behind. You've got to get some level or some degree of coding. There is always going to be need for physical meteorology.
How concerned are you that that's already an area where AI is going to dominate?
It will dominate. And why? Because I know students are using this. I know students are going to ChatGPT and saying, write this code for me. And it's so good.
It's very good.
It's scary good, okay? But if you don't know how ChatGPT is figuring out the code that it's delivering you, woo, that becomes a crutch, not a resource anymore, right? There's a difference between utilizing AI to increase your efficiency in your workflow and using it because you don't know the answer and you need a crutch. Those are two completely different paradigms. And right now, most of the use is the latter. I would rather use ChatGPT in my class to say, have ChatGPT write a weather discussion for next week for Glen Ellen, and then go pick apart where it's wrong, right? How did AI know? What's AI using? How's it gathering its data? How's it using a large language model to be able to distill information in a way? I still think that's going to be super important. Obviously, critical thinking, many of you, man, it's a tie between 1 and 2 for me. Critical thinking and model interpretation is still going to be so important.
Well, that's...
Go ahead. Yeah, go ahead. Jump in, Leon. Comms. Oh my gosh, communication. We're going to talk about communication too. There's so many important things that we're trying to train you to be, but it's not synoptic meteorology anymore.
Well, that's the thing. Even with ChatGPT, if you don't already have an idea of what the answer is supposed to be, and it gives you the wrong answer, if you don't understand that, and you just take it for granted, and you're just, I don't want to say lazy, but you end up being lazy. You don't take the time to understand what the answer should be, or at least the ballpark of what it should be, then it's going to start spitting things out, and you can't determine if it's right or wrong. You just have to go with it.
I see creativity and interdisciplinary collaboration down at the bottom. I want to be very clear is that when you feed these AI models prompts, creativity is a big component of that. And being creative in this type of world with everything out there around us, especially when it comes to data science and coming up with new ideas and new things, I wouldn't just take creativity for granted. It's a very, very important thing. And one thing you'll find out with AI is not very creative.
Yeah, no. If I can interrupt,
Yeah.
Victor, with those prompts, like I think the most advantageous skill you can have is knowing what you're asking the AI.
Absolutely.
When you're forming those prompts, that's where I mean, we've already moved on, but I put expertise pretty high up there because that's what would be leveraging how you utilize the AI or how AI would beat you is knowing what you're asking of the AI.
The best possible use of AI in my case would be like, I'm going to go to AI and I'm going to ask AI to derive theta E for me. I already know what the answer is, but I want it to give me a very beautiful step-by-step derivation that I can hand off to my students. I know the answer, I can verify the answer, but I've now I've created something for my students or something more efficient to help my workflow, right? And that's where I think it's not just AI and weather forecasting, y'all, and you've probably seen this in your own lives. If you do any type of work, AI has probably started to infiltrate into that workflow in many cases, and it hopefully is making your life a little bit more efficient or easier, okay? How about this one? A traditional MET degree is becoming less essential to be successful in the field of meteorology. Do you agree with that comment? And Dom, while we're waiting for responses here, go ahead.
Yeah, my question was about students or people that are going to enter the workforce in the AI era. When it comes down to curriculum and designing this new study path, essentially, what does that look like in your mind when it comes down to kind of going away with the old synoptic, dynamics, meso, and then really hammering home the coding and data science?
I think it's something that you end up having to do on top of the Bachelor of Science degree because we are our hands are tied with the 1340 requirements from the National Weather Service and the WMO that we really can't just go and say, willy-nilly, we're going to remove Physics 1 and Calculus 1 from our curriculum, and now we're all going to take Data Science 1, 2, 3, 4, and 5. We can't do that. There's still fundamental things. You still need to know how to do an integral. You still need to know how to do a derivative, right? You still have to understand, what a cold front is, and if you're talking about atmospheric science. So it's not as easy as just shutting the door and let's take a whole bunch of new classes. We still have to get these fundamentals down, but now it's just tacking on extra things. Look, good meteorologists these days are good communicators, they're good computer programmers, they're good with the physics and the basic fundamental science, numerical weather prediction. They probably have done some sort of AI, right? You have to be like good at everything now to be a good meteorologist. It's becoming unsustainable. Yeah. Gilbert, go ahead.
By having the requirements that the National Weather Service and the WMO have, are we handicapping our students in the AI future?
Yes, absolutely. No question. There's a whole effort within the AMS now called the Mind the Gap. These are trying to get students to bridge between this massive gap that exists between you leaving COD's campus or you leaving Davis Hall and then going into the workforce. The workforce is saying, you don't even know how to code, go back to school. And we're like, no, you've completed your degree, go, right? That's a huge gap, and until we train students with the skill sets necessary, those entry-level positions are always going to be, I think, very difficult, and students will struggle. I would say I'm in the B camp. I agree with this statement. I don't think a traditional BS degree in meteorology is essential to be successful. I don't think it ever was essential. It was obviously a big component to success, but right now, with the way things are, especially the shifting landscape of atmospheric science, if you have a really strong background in computer programming, for example, and a little bit of love for meteorology, I think you're going to be just fine. And finally, what will education and training look like in 10 years? I don't think any of you are going to say A, but you might. Do you think it'll be mostly online with AI-assisted prompts and bots? Do you think education is actually going to go and flip and do a 180 and we are going to go back to these, all programs are going to be very apprenticeship style with strong mentorship and focus groups and less on programs that are widely cast across all universities and they're going to be more a la carte style? Or is it going to be something that we can't even predict right now, something vastly different? And if you put something in D, I'd actually like to hear from somebody in D, maybe somebody from C and D, or even B. I think there are universities right now that are probably in the B camp already. I've taken some AI classes. I feel like they were taught primarily by AI. So, anybody care to speak up about what they think about D or maybe C?
Well, I can only speak to D. 10 years ago, most people weren't doing as much. Well, they were doing all sorts of things on their phone. Social media was still pretty new and on the phone. And as phones became more and more apps and walking around as a computer instead of a phone, a communication device, and it's still going. We don't know in 10 years what that's going to look like as far as the interface. We don't know how integrated this is going to be between meteorology, geology, climate science, which is all the same, oceanography. You get this whole thing going because it all is got to work together eventually, and AI is going to take us there, maybe.
Maybe. I agree with you. I don't think anybody would have predicted 3 years ago that we'd be where we're at with AI forecasts in terms of their skill and speed. So I think it is pretty hard to predict what we will look like in 10 years. The mostly AI assisted, I would say that is something that would be an incredibly slippery slope, and to me would be a big danger zone if we went with B. I do like the idea of smaller groups in apprenticeship style where you're basically in a kind of a mentored group, and it's smaller, digestible programs that are fit for the students' needs and not prescribing coursework across a vast majority of a population. I think that has done some detrimental things to education in the past too. So here's why I think my next exercise is why I think we're still going to, oh, hold on, I lost something. I want to come back to that. Don't do that one yet. We're not going to be able to get to all these tonight, and I apologize because we're running out of time, but I want to show you why we're going to need humans. You're making a forecast for Northern Illinois later today. This is the only map you have. I want you to click on the most important element in making your forecast for Northern Illinois. Pause, stop. You know why we need educators? Take a good look at that timestamp on the bottom. It's a year old.
Excuse me? Sorry.
Yeah.
I had an answer to the question before, and I think it was the, how is AI going to affect, educating? I think the more general a class is, the more it's going to be like an AI-based class, and then for anything specific, say a mesoscale class or something even more special like that, then it's going to be 4 people with one guy who's really experienced with that, who's probably also using AI. So you can't really just say it's going to be a one-size-fit-all to this solution.
Seems to be a lot of people changing their answers now. Maybe the time is the most important thing on this chart. We talk about this a lot in Synoptic. Always make sure you look at the valid hour of the forecast, right? It is one of these things, right, where you can get fixated on the the demonstration here was it's easy to get fixated on the output. And I think a lot of the times we're waiting for AI to give us the answer, and yet it's still very, very important to play that critical role of being the human filter, right? And not forgetting that we are still the ones who programmed that computer, who trained that data set to run on that GPU, to create that forecast, and all of the knowledge that had to be created prior to get to that point. There's a reason we're here. Don't let the computer replace you. And for everybody that clicked up on that front, computer's going to replace you. For everybody who clicked down here, or maybe they didn't click down here because they couldn't see it from the bar, maybe you're in that camp, that's okay too. For all of you that click down there I think that's the hope, right? The hope is that we can still be that filter and understand the most important elements in a forecast and when these models might lead us astray. Okay, I want to get into, we don't have a lot of Weather Service people here tonight. I had some questions about the Weather Service, but in the interest of time, I'm going to move on from the Weather Service. I want to focus a little bit here at the end of my talk, and I'm not going to spend too much time here because I've had an hour of your time already. I want to talk a little bit about the importance of forecast communication. And if you've heard me talk before, this is a really big component for me. It's really, really close to my heart. I think communicating is that last mile in a forecast, right? It's that last piece that takes good information and gets it across the finish line to the user, and not just gets it to the user, but allows the user to make actionable decisions. Comes, yeah. But you know, taking communication out of there, I want to see what some other, right? I mean, if I communicate to you and it's a bad forecast, that's probably not good either, right? So there are various levels of communication or lack thereof. Let's talk about the Texas floods, right? You want to talk about a good forecast? I think I know who's to blame for that particular incident, right? And it's not the National Weather Service. Let's take a look at some of these answers here. We have conversation, learning, usefulness. I love that. A good, successful forecast is useful. Yes. Whoever put that, A+, usefulness. Time sensitive, efficient, comprehensible, timely. I think all those are great. One word that I don't see up here that I would put, valuable. And there's a way to demonstrate that. You can create something called the cost loss curve. What was the cost of producing the forecast and making people take action versus the actual value of the forecast? I think a successful forecast has some degree of value, however you want to measure that. Okay, how about this one? Who is responsible for making sure the public understands the forecast? Is it Gilbert? Is it the National Weather Service? Is it everyone who took Earth 1119 here at COD, Weather Hazards and Preparedness? Is it still the class? Is that still the class number? Okay. Is it the emergency manager? Is the social media police going to come in and make sure that you understand the forecast? I was hoping everybody would be piling on the same answer here. It's not C. No. Who should it be? The public. Gilbert, elaborate. Why should it be the public?
I cannot tell you.
Use the mic.
So sorry. I cannot tell you. I worked at Northern Illinois University as their staff meteorologist for nearly 20 years. I cannot tell you how many times I made a forecast. I made it clear, and I even recommended actions. Hey, we're going to get a storm around 7 p.m. You know, be ready for that. If we had an outdoor festival going on with carnival rides, and I was explicit in all of that. And my forecast was dead on. The storm arrived within 15 minutes of 7 o'clock, and yet they didn't shut it down because they didn't think it was going to happen.
No, I've always said there's a degree of personal responsibility here. And I think, when I used to teach 1119, we talked a lot about personal responsibility. And personal responsibility comes with, I think, understanding the value of weather forecast, but also understanding uncertainty, that not every forecast is going to be correct. And this is a very difficult system nonlinear chaotic dynamic system that we're trying to predict. And there are cases of false alarms, and there's type 1 and type 2 errors and all these things that we need to consider. But there's some degree of personal responsibility that comes with that. And I think a lot of that needs to be done through education. It's very, very challenging, I think, in a lot of ways to present probabilistic forecast information. All right, we did that one. And I think this is it. This is it for tonight. This is my last one, and then we can have maybe a little bit of dialogue. And again, for those of you who want to get out of here, feel free to go. This is the last slide. But we're going to have some conversation, hopefully, after this, a few questions. I want you to finish the sentence. And if you like somebody else's response, you can star it. The The forecast was perfect, but late. I like it. Who put late? Boom. I love that. Forecast was wrong. Forecast is perfect. Well, it's not a perfect forecast. Gilbert was wrong. Who put nobody listened? Yeah, you got it. Nobody saw it, right? Hey, this one right here, that's Texas floods. Forecast is perfect. Nobody got it. Yeah, came too late. Dead wrong. Right? I think you guys get the theme here. That last mile is not just this. Because there are plenty of weather disasters that occur when people still see it. Which tells you what? It has to be able to see it and also force them to take action. That next step is even harder. Right? It's not just this, although in many times it is. But then it's the next step. Hey, I got the tornado warning. Right? I didn't do anything about it, but I got it. So yes, we've had a monumental disaster in Texas where nobody saw it, but there are so many other cases that people see it and still don't take action, which is still a communication problem. It's not a forecast problem.
So I think this is also kind of relevant to what Gilbert said, where it's like you saying, like, I made a perfect forecast. It happened exactly as I laid it out, but no one listened. And up here it's saying, forecast is perfect, but no one saw it, or people did see it and didn't care.
Mhm.
And I think one of the issues we have with forecasting is, I mean, correct me if I'm wrong, but I think there's kind of just a general distrust of forecasters. Not like critically, but it's like, just talk to anybody, any random person on the street. It's like, what do you think about, weather forecasters? Like, they're always wrong, or, you get paid to be wrong every day. It's like,
And I would challenge each one of you in this room, when you hear that type of comment, speak up. It's on you. Otherwise, that's going to be their perception for life, is that atmospheric science is witchcraft. Right? Speak up. Say, hey, did you know our forecasts now are incredibly good out to 7 days? Did you know, right, that AI is actually really, really good at forecasting temperatures? And did you know that AI is helping your flight take off faster and being more efficient at airports during travel? And they're like, really? Yeah, we're actually really good. And you say things like, hey, you remember all of the forecasts that we miss. You remember that one time on your birthday when you're going to go downtown Chicago and it rained and we said it was only a 20% chance. But you don't remember all the other 25 times or 30 times or other 50 birthdays that you've had where we nailed the forecast. Right? So there's a tendency to have that bad rap, right? And it's on us, I think, to fix that. We need to communicate that we are actually good at predicting weather conditions 7 to 10 days into the future.
So when there's people who have that perception around forecasters, what should we say in response to that?
Here's what I say. Because it's usually something of like, well, if you were wrong 3 out of, if I was right 3 out of 10 times in my job, I would get fired. And I go, well, if you were right 3 out of 10 at bats in Major League Baseball, you'd be in the Hall of Fame. Right? You'd be hitting 300, right? You'd be a Hall of Fame. Be a Hall of Fame batter. So I think it's about context. I think you can acknowledge that forecasting is difficult and there is uncertainty and there's times that we get it wrong, but you can talk about the history and how we've gotten really good with technology and how models have advanced and how we're really good now. We're as good now at predicting weather at day 7 as we used to be predicting day 1, right? So there's things I think you can tie back to build trust. And hopefully, I think I do see a good job of our broadcasters around here in the Chicago market of doing that. They're good forecasters, and I think they discuss that type of skill.
What I
Paul,
always
and then we'll go.
What I always like to say to people who don't believe that, I go, well, it might be where you're getting your information. If you're using this, you're getting nonsense. And you're like, well, it was 42 degrees and it's going to rain at 3:08 p.m. It's like, then they're giving a false expectation of what they should expect. Yeah. So I think that's a problem.
I agree. We had another comment in the back.
Francis Bacon, the source of myth with mankind is the fact that people notice when something hits, but not when it misses.
Exactly. That is perfect. How many people have always said, well, the storm always goes around me, never hits my house? Well, yeah, probabilistically, guess what? If this is your house and this is a grid that represents all of your neighbors around you, right? And we're just going to throw a random dot and you understand probability, how many times is that random dot going to hit your dot in the middle? If we just take a random distribution, right? It's going to, majority of the time, it's going to be missing you. Okay, and it's going to seem like it's always around you because this is your home. But you say, hey, my neighbor got hit, I didn't. My neighbor got hit, I didn't. My neighbor got hit, I didn't. There's only a 1 in 9 chance that you're going to get hit, right? 8 out of 9, somebody around you.
I think what you're describing is the problem that the public expects a deterministic forecast every single time, and that is not, we're moving away from that actively.
Yes. There's limitations, right, to what we can do in terms of
do you
deterministic
think,
forecasts.
I don't know, I guess it's kind of a loaded question, but it's like, do you think that's a problem that can be solved? It's like, do you think you could, through like, you know, education or whatever, do you think it's possible to like move the public away from expecting a deterministic, it will rain at 3:08 p.m. forecast, or do you think that's kind of just a problem we'll always have to deal with?
I think it depends on the stakeholder, and I'm going to give you an example. There's plenty of cases where a probabilistic forecast is very valuable. If I told you there was an 80% chance that we were going to have a colder winter this, and I'm not saying that there is, but let's say that there's an 80% chance that we're going to have a colder than normal winter, and we're going to have 20% more HEDDs across the Chicagoland area, like that probabilistic forecast could be a financial decision that could be very beneficial to you, right? There's going to be other stakeholders that require a yes or a no. Do I need to suspend tomorrow's parade? I can't do that if you tell me there's a 20% chance unless I have a clear binary decision threshold that says I'm going to take action when your probability gets to 51%, right? Or I have enough tolerance where I'm not going to take action until your probability is 95%, right? And so every stakeholder is going to have that sliding level of decision making, which is binary, that's going to be maybe sliding probabilistic scale. That doesn't occur until something says, I have to make a decision. And this is one thing that is so interesting to me is how people come to that number. How do you arrive at 80% probability, and that's where you're going to call it, right? So I think there's challenges. Like, and there might be, what if there was a 2% probability that we'd have an F5 hit a nuclear reactor? Would you be willing to take that risk? Well, I think they're rated F5 and greater, right? There's some risk tolerance that no matter the level, even anything that's non-zero is unacceptable. And that is all in the decision maker. And I think that's why probabilistic forecasting is so beautiful, and that's why we need to embrace it. It's just that stakeholders that have to make decisions are typically making binary decisions, and their binary decisions are somewhere on that scale. And unless you communicate with them to understand where that is on that probability scale, you're probably missing that entire communication piece that we just talked about. Okay? All right, I know we went really long. We're now, I think we went, well, I think after the intro, we probably went an hour and 15 minutes. So I want to thank you all for coming. We could do this for hours. I love this kind of stuff.
Yeah, this
thanks,
is great.
Paul, for the invitation.
I think we
And,
should do this more often. Maybe we can get another fireside chat in March when we might need
be warmed
more
up
wine and
after
more
we have
fires.
a couple feet of snow on the ground.
So please thank Dr. Gensini again.